So okay, we now continue with Tverberg theorems, now optimal colored Tverberg theorems for prime powers, and now actually it is now realized this is a topic very close to LV3 divisions. Maybe not obviously, but okay, but the methods are actually very similar. So okay, Rade, you may start.
Thank you very much. Can you hear me? No problem with the with the sound. You can hear me. Okay. So first of all, thank you for a very pleasant opportunity to speak with for the audience of my colleagues and friends and some new people. And this is based on joint papers with Gane Panina, with my friend from University of Banja Luka, Duško Jojić. And I wish I were in Moscow and to deliver this lecture in person, but I hope maybe next year or maybe this year there will be more opportunities. So the title, Optimal Colored Tverberg Theorems for Prime Powers, as already mentioned, this is related to many talks which we heard today. And I hope to actually, I will not be very technical, but instead I will try to give you an overview, some inspiration you hopefully can find, because technology itself can be, of course, demanding at some points and not very inspiring. So optimal Colored Tverberg theorems for prime powers. So let's see, what is it about? We already heard about topological Tverberg theorem. So originally proved for primes by Imre Barany, Senja Schlossman, and Andras Sic, and also by Murado Zaidin, but it was unpublished. So Volovikov, Sarkaria, and Marc de Longueville independently found the proof for prime powers. So what is the usual formulation of this theorem? You have a continuous map. You have a continuous map from a simplex of dimension r minus 1 times d plus 1 into the Euclidean space of dimension d. Then you can find r disjoint faces of this simplex so that they overlap in the image. So the image intersects. So this is topological Tverberg theorem. If F is an affine or linear map, then you obtain the classical affine or linear Tverberg theorem proved by Helge Tverberg himself in the 60s. Now, this concept was already mentioned by Arkady Skopenkov. What does it mean for a complex, implicit complex, to be almost R-embeddable? So we know, of course, you already maybe remember the definition, or we know what is embeddable in the usual sense. So it is one-to-one continuous map, which is homeomorphic to the image or something like that. So we want to say that something is embeddable in some sense if there are no points that are mapped to the same point. It is R-embeddable if there are no R-fold points. But if you have a simplistic complex, then you say there are no R-fold points which are far apart. In other words, they belong to disjoint simplices delta 1 up to delta r. So almost R embedding exists if this intersection is empty for any collection of pairwise disjoint simplices. And then we say K is not almost R embeddable if such an R embedding does not exist. Almost R embedding does not exist. Well, sounds maybe complicated for non-initiated, but I will show you some examples. By the way, if we have this definition, then topological Tverberg theorem can be just simply stated as the statement that the simplex of this dimension, r minus 1 times d plus 1, is not almost R embeddable in RD. So you see, it is too big in some sense, and then it does not allow you to map it without R points overlapping in the image. And here are some familiar examples. First of all, I need some definition, but quite natural, of interesting simplicity complexes. First of all, KPQ is a complete bipartite graph, which has, in topological terms, it is the join of two sets, P element sets and Q element sets. So it's complete bipartite graph. And now, what would be a simplicial complex, which generalizes the concept of bipartite graph? It is complete multi-partsite simplicial complex. So you have K plus one discrete sets and take a join. So it can be also described as a hypergraph, which has at most one point from each of these color classes or something like that. And now, once we have these definitions, then we have already very interesting examples. For example, one of Kuratovsky's graph, K33, complete bipartite graph with 3 vertices on each side, is not almost too embeddable in R2. So it is related to its non-planarity. But for us, here are probably even more interesting higher dimensional analogs. So you can informally say that what are we doing? We are studying higher dimensional analogs of non-planarity. And ideally, it would be nice to have complete characterization of higher dimensional of non-almost R embeddability, similar to Kuratovsky's criterion for non-planarity. But so far we have only examples, or most of the time we deal with examples. For example, Barany and Larman proved that this two-dimensional complex, which is K33 join of 3 copies of 3-element set, it is not almost 3 embeddable using only linear or affine maps. But now, if you want to use, if you want to map into 3-dimensional space, then you need bigger complex. It is K555. It is not almost 3 embeddable by any continuous map. And K4444 is not almost R embeddable in R3. So these are all examples of the colored Tverberg, of different type of colored Tverberg theorem. So what is the colored Tverberg theorem? Well, let me just quickly remind you, topological Tverberg theorem can be also described as a monochromatic, only one color. But now if you color the vertices with different colors, for example, you have K plus 1 colors, you have a simplex of dimension n, and you color the vertices, then you have a restriction. You do not allow faces which have more than one vertex of the same color. These subsets of the vertex set, which have at most one vertex in each color, are called the rainbow simplices. And then it's really a moment reflection. You can see that the simplicial complex of all rainbow simplices is exactly K T0, T1, and up to T sub K. So the complex we just introduced, maybe the slide before. And one way to ask what is colored Tverberg theorem or colored Tverberg problem, it is the following problem. Now the terminology we introduced allows us to use this elegant language and say, what is colored Tverberg theorem or problem? It is the question, characterize all complexes which have the property that they are not almost R embeddable in D. So you have parameters, you have dimension of the ambient space, you have this overlapping number R, you have these cardinalities of the colors, and then you ask for which values of the parameters you will have a positive result, non-embeddability result. And here we have some examples. So these are some examples. You can formulate it in some language. For example, K555 is almost 3 not embeddable, is not almost 3 embeddable. You can rephrase as follows. You have 5 stars of red color, 5 stars of blue color, and 5 stars of white color. Then you can always find 3 rainbow triangles which intersect in a single point. So it's some sort of constellation. Okay. And these are 2 main examples of Colored Tverberg theorem. Type A was proved by Pavle Blagojević, Benjamin MoCCA', and Günther Ziegler. It was published in 2015, but it was already available as a preprint in 2009. So it simply says that if you have this simplistic complex K-R, so you have D+1 copies of set of cardinality R-1, and you have just a single point, take this join. So it is join of D+1 copies of zero-dimensional complex R-1 and a singleton. Then it is not almost R embeddable in RD. So I call it here type A. Pavle, Benjamin, and Günther often call it optimal Colored Tverberg theorem. Here is type B theorem proved by Siniša Vrečica, my Belgrade colleague and friend, and myself in 1993. Now here in type A theorem, the assumption for the overlap number is that it must be a prime. Here the overlap number is a prime power. And here you have additional condition. Well, this is what distinguishes type B from type A theorem. It is that the dimension of rainbow simplices is strictly smaller than the dimension of the ambient space. Then this simplistic complex, you see the number of points in each color is bigger. So it is obtained as the join of K+1 copies of the zero-dimensional complex. It is not almost R embeddable in RD. So if I go back to these examples, then it is easily checked that examples number 1 and number 3 are type B theorems, while example number 4 is type A theorem. And what is the difference, the obvious difference? Here, for example, in type B, the dimension of the simplistic complex is 2. And you can have at most 3 triangles intersecting in dimension 3 if the ambient space is of dimension 3, while in type A, the dimension of the simplex is 3, exactly is the same as the dimension of the ambient space, so you can have a larger number. So these are different results. We classify it as type A and type B because we don't often call it optimal Colored Tverberg, because all these theorems are optimal in their own kind. For example, the simplest example of the type B Colored Tverberg theorem is this Kuratovsky's result, saying that K33 is not embeddable. And we know if you take only K2 1000, if you take 1000 points in one color and only 2 in another color, then you can embed it. So this is optimal. Already this result is optimal. K55 is also optimal in the same sense, and so on. Okay, so this is a brief history of Colored Tverberg theorem. And you already heard that the name Colored Tverberg theorem appeared already in the previous talk by Gaine Panina in connection with NV3 divisions, but also earlier Arkadis Skopenkova, I think, probably mentioned them in the context of almost or almost non-embeddable. So you can ask, okay, this is world development. How we proceed? What is known, what is not known? And now it is obvious, for example, from here, maybe the main open problem is the following. We know already that that overlap number R must be a power of a prime. Otherwise, there are counterexamples. And this is part of the exposition of Arkady Skopenkov, and the names mentioned are Mabilar, Wagner, Blagovic, Frick, Ziegler, Skopenkov, Ozaidin, Gromov, and possibly other people. So power of prime is something that you cannot remove. And that's why it appears in type B theorem. But look, in type A theorem, it's just prime number. It's just prime number. So is it possible that type A theorem, as it is here, is correct if R is a power of prime? And the answer is we don't know, I think. What does it mean? Well, it means that you prove these results, you obtain positive results by applying topology, reducing it to equivariant topology, but it doesn't work the other way around easily. Actually, the great success of Mabilar and Wagner and other people was that they were able to construct this triple or higher order Whitney trick. And it does not exist so far in this kind of theorem. So this is a major open problem. Can you construct for this type of complexes some sort, prove some Whitney trick reduction and obtain a counter example? So that's a major open problem. On the other hand, what about prime powers? Is it possible that this theorem actually holds for prime powers? So these are questions. So this is something that I wanted to keep in mind. And also I want to keep in mind what happened, why we needed in the first place Colored Tverberg theorem. And the answer is it appeared very naturally. Actually, this is a reminder just for me, these two slides. These are just clips from some papers. The first two clips are from the paper by Günther Ziegler in Notices of American Mathematical Society. This clip with problems is from the paper by Imre Baraň, Zoltan Füredi, and Laszlo Lovaas, where they actually conjecture the existence of Colored Tverberg theorem without saying any bound, anything except that such a phenomenon exists, more or less. And the reason they were interested in that, it was discrete computational geometry. And the book of Jerzy Matoušek is very good, still very good source of information about that. And this is a clip from that. For example, Lovaas, Baraň, and Füredi were interested in this halving sets problem, asymptotics for the number of halving hyperplanes for a finite set of points. This is K-set problems closely related. Then there is piercing problems and so on, so of discrete computational geometry. And Colored Tverberg theorem played originally important role in all these problems. So to summarize, power of primes, I would like to know more about power of primes. And second, I also want to find motivation in discrete problems involving clouds of points, involving finite sets of points. By the way, here I remember that theorems come and go, but good example is always a good example. That's a good saying. So if you study mathematics, it's not a bad idea to say, if you want to find motivation and to understand better, it's a very good idea to try to understand one example and then another and so on. While theorems may be sometimes difficult to comprehend, and sometimes they are improved, especially proofs are improved. Okay, so here is one example I want to discuss with you. And it illustrates more or less all Tverberg, continuous Tverberg and colored Tverberg theorem I mentioned so far. So what do we see here? We have, this is a three-dimensional picture, but you can imagine you have a d-dimensional Euclidean space, and you have this many colored points. So we have a simplex, d-dimensional simplex. In this picture, it is a three-dimensional simplex. Barycenter is this black dot in the middle. So this is the barycenter. And now each vertex, in the vicinity of each vertex, you have a cloud of points. More precisely, you have p prime number minus p to the k prime power minus n number of points in each color. So here it's yellow, red, blue, and green. So they are forming together d+1 monochromatic clouds of points, and they are all concentrated near the vertices of this d-dimensional simplex. And now you ask, can you find Tverberg point? You remember Tverberg point, you partition, in this case, R is equal to P to the K, so this overlap number is P to the K, and you want to partition this set into R disjoint, well, maybe rainbow sets, and so that they overlap. And now I will go slowly, offer you three scenarios for this example. First of all, what if we forget colors? So the colors are gone. Now we have, and also the overlap number is arbitrary in this case. I hope you can see the bottom of the screen. So if not, tell me so I can read you aloud. So you have R minus 1, D plus 1 plus 1 points in RD in this very special position. So I emphasize, this is not arbitrary collection of points. You have a simplex, you choose a simplex, you choose the barycenter, it is one of the points, and then place in each vertex, in the close vicinity of the vertex, you place R minus 1 points at each vertex. Altogether, you have R minus 1 times D plus 1 points. But there are no colors now. So now there are no restrictions of having rainbow simplices. And then you see that there is Tverberg theorem holds. But the Tverberg theorem, original linear Tverberg theorem, says you allow any scattering. You can keep one point fixed, for example, if you like, but you can just randomly distribute all other points in the space. And then monochromatic Tverberg theorem says whatever you do, you will still be able to find a partition into altogether R disjoint sets so that convex hulls overlap. So this is what I summarize here. You have this number of points, overlap number I is arbitrary, you have unconditional scattering of points, and the conclusion is there exists a Tverberg point, a point which is in common point for the common convex hulls of a partition. Now back to the colors. I want to tell you what, informally in this example, from the point of this example, what is type A colored Tverberg theorem of Blagojević, MoCCA', and Ziegler. Again, you have this particular configuration, but now you have colors. Now you have a strict condition. You do not allow arbitrary faces, triangles, or simplices. You allow only rainbow simplices. But you allow, as in the previous results, unconditional scattering of points. So you take yellow points and distribute it anywhere. Red points the same, blue and green points as well. But now you need a condition. P must be a prime. So the number of points in each color is a prime number minus 1. Then you have a conclusion. You have rainbow simplices. the rainbow simplices, which are the pairwise disjoint, so that convex hull intersect. So this is type A Colored Tverberg theorem. And now a new result. So you remember I asked what can we say for prime powers? Is there Colored Tverberg theorem for prime powers? And our answer is, as I said, it is a joint work of Duško Jojić, Gajane Panina. Our answer is yes, there is a result of this type which is also optimal and which also includes Colored Tverberg theorem of Blagojević, Mačka, and Ziegler as a special case. But you have to pay. There is a price. And I'll explain, I will explain what is the price. But hopefully this is a picture is nice. It is like fireworks. So maybe the price is not that bad. So look, R is a prime power. So now you are more general. The number of points is the same. The coloring is the same. You again put the points at the vertices as clouds at the vertices of a simplex. And the conclusion is the same, but the scattering is restricted. Actually, you assume that these clouds are actually infinitesimally close, that the points are very close to each other, so close that you don't distinguish them. And they are allowed to scatter in clusters. So each color has R-1 points, and then I will explain in the next slide exactly what kind of clusters are allowed. So you can distribute, you cannot arbitrarily scatter all points. Instead, you made small or slightly bigger clusters and then randomly distribute them, and then you have a conclusion. So this is difference. So just for your satisfaction, there are the monochromatic Tverberg theorem, type A Colored Tverberg theorem, and multiset Colored Tverberg theorem. Why we call it Colored Tverberg theorem, multiset Colored Tverberg theorem? Because these clusters, these small monochromatic clusters, can be also interpreted as single points with multiplicities. So each of these small circles in color is actually maybe interpreted as a single point with certain multiplicity. So they create a multiset. So set, as you know, of course, is points are all either present or non-present. But in multisets, points are like in divisors in algebraic geometry, points are present with some multiplicity. Let me just check. I started at 5 minutes past 2, and I speak 40 minutes. So I think I have 10 more minutes.
You have 10 minutes at least, maybe 10, 11, 12 minutes.
Yeah. Okay.
You have 10 minutes at least. Yeah, 10 minutes.
Yeah, very good. Thank you very much. So my objective was really to tell you, to even for those who are not familiar, who were not familiar with Colored Tverberg, or who are not familiar with some deep technology from algebraic topology, to see from these examples that the geometry of this picture is quite natural and not intimidating. Of course, technology you apply can be more demanding, but it is also naturally developed in a sense from these problems. Okay. By the way, I like to dream about possibilities, even though sometimes they maybe doesn't seem not very convincing. So I say aloud in front of you, is it possible that there exists p-adic combinatorial geometry? Because these clusters are powers of a prime number p of certain type. And we know it will turn out that we have p-1 clusters of givens in each given size, and then well, I cannot see unfortunately the bottom line of my screen because it is covered. Let me see if I can do something. Well, okay, it's not so important. So what about p-adic combinatorial geometry? And here is the formal statement. That's exactly what I told you about the scattering of clusters, formulated as a formal mathematical statement. So now we have a prime number. You have number k p plus 1 d plus 1, and it will be dimension of a simplex, and you have a partition of the vertices or coloring of the vertices of simplex, but then each of these sets has p minus 1 times k vertices, but each of these sets has a multiplicity, and multiplicity vector is this one. It is powers of primes, and it holds for all these colors C0, C1 up to CD, except the last one, which is a singleton, which is its own single color. And what is the statement? The statement is very similar, but with an important difference. Under these conditions, for any continuous map, there exists R, but look, not necessarily disjoint or even different faces. So now we allow, look, this is really a sharp distinction from the standard Tverberg or continuous or Colored Tverberg theorem. Now we have a smaller number of points, but now we allow simplices to overlap. But the number of occurrences of each vertex in all faces does not exceed the prescribed multiplicity. So they are allowed to overlap not more than we prescribe in advance. Then we have the usual conclusion. The usual conclusion is that we have rainbow simplices so that the images intersect. Keep in mind that in a special case, when we choose parameter k to be equal 1, then we obtain the result without multiplicities. So in some sense, we included Colored Tverberg theorem of Blagojevich, Mačka, and Ziegler into a family of results. But these results, most of them are about multisets of color points. And now, since, yes, I have a little more time, I want to tell you about how these results are proved and why chessboard complexes are important. A chessboard complex appear in the proof of, originally they were constructed really by Siniša Vrečić and myself for the proof of type B Colored Tverberg theorem. And it turned out that we needed a statement like statement number 7. It says, whenever you have a chessboard complex of the size 2r minus 1 comma r, and you take this join, then there is no equivariant map without zeros from this join into some Euclidean space. For this occasion, it's not really necessary to explain in greater detail. So this is type B theorem, and type A theorem is very similar, except we use here a different chessboard complex. Remember, Gayane Yurevna, she used this chessboard complex for a new proof of Avakumov-Karasyov result, NV3 deep result, which generalizes Gale's theorem, while she also used this chessboard complex for a proof of a new NV3 result of different type. So these are all standard or classical chessboard complexes. Now, in order to obtain a multi-valued Colored Tverberg theorem, which I just explained, this scattering clusters point, you need a statement, similar statement, but more complicated. Here you need also something like chessboard complexes, but these are so-called generalized or multiple chessboard complexes. they are also based on a chessboard, but then you allow more rooks in rows or in columns, but it follows a special pattern. So here is I think, yes, so this is the key result about the degrees of maps. So you remember that degrees of maps is a very efficient method for proving, well, maybe more Ulam type theorems, but also can be used directly. So our result really follows from the following from the following theorem, which says this pseudo-manifold with singularities with high codimension, with group action, has the property that when you map it equivariantly to this sphere of this dimension, the degree must be non-zero. So here, this is the main technology we use. This can be described as Eilenberg-Krasnoselsky theory of degrees for equivariant maps for non-free actions. And a canonical reference is this book by Kushkuli and Balanov, Geometric Methods in Degree Theory for Equivariant Maps. And let me see what, yes, these are the references. I have just a couple of minutes to make final remarks. So the second paper is our earlier paper, where we applied this technology by this Eilenberg-Krasnoselsky theory in the way developed by Kushkuli and Balanov in this book. And as a result, we obtained only partial results of this type. And later on, we were able to extend Kushkuli-Balanov's argument and to show that it actually applies not only for topological manifolds with group actions, but also to topological manifolds with singularities, if singularities are or sufficiently high codimension. And this led to the main theorem, which I described to you in this lecture. And there are some special cases, just to give you an idea, that special cases look like, well, hopefully interesting results about clouds, colored clouds of points. For example, you have a set of 7 points, and this set is colored by 4 colors. The first two numbers, the first two elements are colored by red, and then by blue, and then by green, and vertex 7 is white. And then you have 6-dimensional simplex, so vertices can be identified as 1, 2, up to 7. And the statement, the special case of the result I described, says that for each continuous map of the 6-dimensional simplex into the plane, you can always find 4 faces of this 6-dimensional simplex such that the images overlap, they have non-empty intersection, all of them are rainbow, that is, each simplex contains at most 1 vertex from each of the pairs. And each vertex occurs in all faces for k odd at most once. And for k even, I think, let me see, for k even, it can occur twice. So you have this distinction with the usual situation you see appears precisely in the last condition. And just for comparison, this result can be, it is related to these conjectures. These are the simplest, probably open. I think they're open problems. I think we don't know if K33 is almost 3 embeddable in the plane. We know from Baranin and Larman that such an embedding, which is affine, does not exist. And we don't know, this is a stronger result, I doubt that it is true, that K3331 is almost 4 embeddable in the plane. We don't know that. And this is a similar statement which a corollary of our result, which proves this result 10 for a very special maps. So we cannot prove it, we don't know, we think this is not true, but we can prove it for some special class of maps. And this is just the final slide, just not to go over time too much. So this is just to illustrate this degree theoretic statement. A special case of the result we had to prove. It says that there does not exist an equivariant map from this generalized chessboard complex, which I haven't had time to talk about, into this sphere. And I just want to emphasize here that these are perfectly concrete chessboard complexes, similar to what Gane explained in her lecture. And what we see in this image is, well, I will not, of course, go into details, but I'll say that from this image, you can derive a triangulation of a boundary of this cube, a dissection of the boundary of a cube into 12 triangles, and you obtain a triangulation of 2 spheres, and it turns out that this chessboard complex is just a 2 sphere. And then you have 2 spheres to the third joint power, it is S8, and this result essentially says that with respect to the Klein group action, the 8th sphere joint 4 cannot be mapped equivariantly to 8th sphere, and of course it is correct. Well, thank you very much for your attention. I hope this was thank you for your patience and attention.
Oh, thank you.
I'll stop.
Okay, so any questions?
I usually ask also emotions.
So I want
Are you angry?
So in this case, okay.
Sorry? Yes, go ahead.
Okay. So I mean, in this situation, it turns out a manifold, but generally those complexes are not manifolds, not student manifolds. Yeah.
Precisely. That was one of key technical steps, that to find out which generalized chessboard complexes are pseudo-manifolds. So you need something that carries Euler class, and then you can talk about degrees of maps. So for that you need pseudo-manifolds, and then by using that analysis you find out an interesting class of chessboard complexes which are pseudo-manifolds. Yeah, that's precisely what we need.
Okay. Okay, so we make a short break, maybe I don't want 3 minutes or.
Yes.